Okay. The first algorithm, quantum algorithm we'll discuss is Deutsch's algorithm. This algorithm was introduced by David Deutsch. You know, he's one of the founders of quantum computation in 1985. And I think arguably this is the first quantum algorithm, that is introduced. Of course, at that time in 1985, there was no quantum computers. There was no capability to build qubits and manipulate qubits. But still, people were uh, through the motivation, given by earlier scientists, like as we discussed, Richard Feynman in 1982 and others, people were visualizing, algorithms. They were thinking, let's suppose we have a quantum computer. Uh, for what purpose quantum computer would be good for? I mean, what kind of an advantage, one could obtain by building, such a computer? These early algorithms, they don't necessarily have practical use, but they illustrate certain advantages or certain speed up with respect to classical computation. Uh, and some of the uh, more recent algorithms like Shor's algorithm and Grover's algorithm that we'll discuss, they use the ideas from these early algorithms. So the first algorithm we discuss is Deutsch's problem. The Deutsch's problem is very simple and also not difficult to understand. Let's suppose we have a function, a mapping from 2-bit, from a single bit to a single bit, right? So I have 0 and 1 mapped to a 0 and 1. And let's illustrate this function like this. Again, as a black box. In the input, we have x, and in the output, we have f of x, right? This mapping. So here are all 4 possibilities of this kind of a mapping, right? There are only 4 possibilities. These 4 possibilities are represented here. Like, for instance, the input is always 2 possibilities. It could be a 0 or a 1, and the output also could be a 0 or a 1. But these first 2 possibilities, we call them a constant function. In other words, the output, these input 0 and 1 bits, they are mapped to a constant value. It's a zero, either a 0 or a 1. Like in this first possibility, for instance, if the input is 0, it's mapped to 0. If the input is 1, it's again mapped to 0. So another possibility would be the input 0 is mapped to 1, and input 1 is also mapped to 1. So for obvious reasons, this is called the constant function, right? Because regardless of what the input is, right, you have a constant value in the output. So this is one class of possible functions. Another alternative would be what we call a balanced function. In other words, f of 0 is different from f of 1, right? In the input, again, if you have 0, the output could be f of x could be 0. If we have 1, f of x could be 1. This is one possibility. Another possibility is for x equals 0, f of 0 is 1. For x equals 1, f of 1 equals 0, right? So in this case, we have f of 0 is different from f of 1. This is called a balanced function. It's balanced because in the output, the number of 0 output and the number of 1 output is equal. In this case, it's 1. But we'll see, in more higher dimensions, we'll have more possibilities. So this is what a balanced function is in this case for a single qubit. So we are given this black box F, right, here over here, but we do not know which of the 4 possible functions, this F represents. The objective of Deutsch's problem is to determine whether it's a constant function or a balanced function. In other words, whether f of 0 equals f of 1 or f of 0 is different from f of 1. So we want to classify, this circuit. We don't know this circuit, but we want to classify this circuit, whether it's a constant function or a balanced function with minimum number of queries. Classically, it's easy, to see that we need a minimum of 2 queries, right? We need to compute f of 0 and f of 1 in order to be able to definitively know whether it's in this class or in this class. So minimum number of queries that we need is 2. F of 0 is 1 query, and f of 1 is another query. But we'll show quantum mechanically, we only need a single query to identify the circuit, right? We also note that f1 of x over here and f2 of x, they are not unitary, they are not reversible, right? I mean, just by knowing the output, there's not a single mapping, to the input, so they are not unitary. However, the oracle construct that we use over here is unitary. That was the whole idea, remember, to build a bit oracle, was to convert an f, a classical function f, to a unitary operation. So oracle, as we said, can be seen as a controlled f function, right? In the input, you have b as an ancilla bit, and a as your control bit. So in that sense, an oracle can be visualized as a controlled f function, right? If this control bit a is f of a is 0, then b plus 0 is b. If f of a is 1, then b plus 1 is reverted, right? B becomes b inverse. 0 is converted to 1, 1 is converted to 0. So in other words, we can represent this unitary construct, oracle construct, like this. Classically, this circuit, this classical circuit, can be used to compute whether we have a constant function, defined like this, or a balanced function. How can we do that? Right? Let's suppose in the input we have 0 and 0 values, and we have over here f of 0 XORed with 0, and then there's a NOT circuit which converts this 0 to 1, and then we have again this f function, and in the input we have 1, so this is converted to f of 1. So in the output, right, we have this 0, and then through this NOT gate, this 0 is converted to 1, and then 1. But on the target bit, right, we have f of 0 plus 0, right, over here, f of 0 plus 0, and plus f of 1 plus 0, right, which is equivalent to f of 0 plus f of 1, because 0, doesn't change the output. So this circuit computes f of 0 plus f of 1. And this is equivalent to saying, whether f of 0 equals f of 1 or f of 0 is different from f of 1, because as we know, f of 0 plus f of 1 equals 0 always, right? If f of 0 equals f of 1, because 0 plus 0, right, equals 0, and 1 plus 1 equals 0. And else, in all the other cases, we have f of 0 is different from f of 1. So this, as we see over here, classically, this circuit needs 2 queries. One query is over here through this f function, and another query is through this f function. Classically, we need 2. I mean, it was obvious, to see this, but this classical circuit also needs 2. I mean, naively, if we convert this to a quantum circuit, right, by changing this NOT gate to an NOT operation to an X gate, and using this controlled F gates, right? In the output, we would measure F0 plus F of 1, F of 0 plus F of 1. But this quantum circuit also requires two Curies, right? This is one Curie, and this is two. This is the second Curie, and this is the measurement. So, I mean, just by naively, converting a classical circuit to a quantum circuit by replacing the corresponding gates did not produce any benefit as compared to the classical case. But the advantage of quantum computation is that in the input, we do not necessarily have to use the standard basis, ket0 and ket1, right? I mean, the advantage comes when we use in the input the superposition states. The use of superposition state in the input is actually brings the advantage. That implies, in some sense, we compute ket0 and ket1 simultaneously and see how this works out. Let's see. So let's suppose now, again, we have ket0 and ket1 in the input, but now we also have Hadamard operations, Hadamard gates, right? To convert this ket0 and ket1 to ket plus and ket minus superposition states. And we apply the phase oracle that we discussed previously. And again on the first qubit in Hadamard, and we make a measurement. So let's analyze, the circuit, how we can use the circuit to achieve some speed up, with respect to the classical case. So this first stage is easy, right? Ket0 is through the Hadamard operator is converted to ket plus, and ket1 is converted to ket minus. Now, since the ancilla bit is ket minus, right? This is a phase oracle. Remember, phase oracle was one when we have the ancilla bit. This bit is as ket minus state, and we had discussed the output of the phase oracle was -1 to the f of a, right? Ket plus state, because ket plus is ket x now is in the input, and tensor with ket minus. This is the ket minus state. So this state tensored with ket minus. This is now the state in the output of the phase oracle. But now let's see what happens when we apply an Hadamard on the first qubit, and Hadamard on the first qubit, right, would convert this plus to a zero state, right? So at this stage, over here, after this Hadamard, we have -1 to the f of a ket 0 state. And when we make a measurement on this, right, on the standard basis, let's see what happens. So -1 to the f of a, if we measure like these in these four possible functions, if we measure f of x, if it is 0, right, like in this first case, remember we had four possible cases, of 1 bit to 1 bit functions. And this was the first case. In the first case, as you see, f of x is always 0. So this phase over here on top, right, -1 to the 0 is always 1. So we have the state ket plus, right? And similarly, in the other case, when f of x equals 1, right, the output is f of a is always 1. So -1 to the 1 is -1. So we obtain the minus plus state. So if for the case when f of x is a constant function, we have in the output plus minus plus state for constant function. Similarly, if you do the same computation for the balance functions, like for the output is depending on input 0, 1 or 1, 0, you would obtain a plus minus minus state, right? In the output over here. So if you apply a Hadamard on plus minus plus state, you would obtain right a plus minus cat 0 state, right? Now over here I have plus minus cat plus state. So if we apply an Hadamard on this, this plus state would be converted to a 0 state, but the phase in the front remain, plus minus 0. So after the measurement, right, cat 0 state, if you do a measurement in the standard basis, cat 0 would be 0. So in the output, if you measure, right, a 0, that means you have cat plus state. And similarly, cat minus state, right over here, cat minus state that corresponds to the to a balanced function. If we apply another mark, you would obtain this minus state would be converted to a plus state, but with a phase plus minus 1, in the front, plus minus 1, plus minus cat 1 state. And if you again apply another mark on this and make a classical measurement, you would measure a 1. So what we can conclude is, therefore, if the output is 0, right, after the measurement over here, if we measure a 0, then it's a constant function. In other words, f of a equals 0 or f of a equals 1. If the output is 1, then this is a balanced function. F of a is different from f of b, and it's a balanced function. So we, using this circuit, this construct, we were able to classify this function, f of x, whether it's a constant function or a balanced function, using only a single query, right? I mean, classically, we had to have two queries to identify f, whether it's a constant or a balanced function. So this algorithm, it's not a necessarily useful algorithm, but this is the first algorithm, that demonstrated some speed up with respect to a classical algorithm. Two measurements in classical case versus a single measurement in the quantum case to identify whether the function is a constant function or a balanced function. This is the second early algorithm that we discussed, which is called the Deutsch Josza algorithm. This was introduced in 1992. It is, in a sense, a generalization of the Deutsch's algorithm we just discussed. The only thing is now we have an n-qubit system instead of a single qubit to single qubit mapping. We have an n-qubit system, and we have a mapping, n-bit string mapping to a single bit, right? And this time, the purpose of this algorithm is to decide whether this function f of a is whether it's a constant function or a balanced function, and with minimum number of queries. And we'll see that there is an exponential speed up with respect to the classical case through this algorithm. So let's define once more what we mean by a constant function and balanced function. Here's an example. These are the possible inputs, input values for A. 3-bit, all the possibilities of 3-bit in this particular example states. And f1 of A and f2 of A, they are constant functions because we map all these values in f1 of A to 0. And in the case of f2 of A, we map all these possibilities to a constant value 1. So these are called constant functions, f1 and f2. A balance function, remember, is the case when we have the number of zeros and ones the same, right? I mean, in this case, this is an example of a balance function. That could be many balance functions. We have, for these values, we have the output 0, and for these values, we have the output 1, and the number of zeros and the number of ones in the output, they are equal. So we call this kind of a function balance function. Obviously, there are many other functions that are neither constant, neither balanced. But for this particular example, we only consider a constant function and a balanced function. And the purpose of this algorithm is to deduce whether this function is a constant or a balanced function with a minimum number of queries. For n qubits, there are, of course, 2 to the n possible values for f of A, because there are 2 to the n possibilities, right, in the input, and there are 2 to the n corresponding values of f of A. And the number of balance functions are 2 to the n choose 2 to the n over 2, right? Because half of them, right, 2 to the n, there are 2 to the n states, and you want to choose, pick half of them, which is 2 to the n over 2, to be 1 or 0. So that's what makes this function a balance function. As you see over here, this the size of this table scales exponentially in n. There's a 2 to the n, so this scales exponentially. So classically, if you look at it classically, how many queries one would need to determine whether this function is a constant function or a balanced function? I mean, we would need, right, to definitively know the answer, 2 to the n over 2 plus 1, right? 2 to the n over 2, remember, is half of the possibilities. There are 2 to the n possibilities in the output, but 2 to the n over 2 is the half. So we just need to, just to make sure, an additional query or a measurement, just to make sure, that we have a constant function or a balanced function. Like, for instance, one could have 0, 0, 0, 0 up to the half, for values, but we don't necessarily know what the next one will be. So we need to make a second measurement, an additional measurement, to make sure, that we have a constant function like this or a balanced function. So classically, this is the answer. And as we see over here, again, the number of queries scales exponentially with n to be able to identify whether this function is a constant function or a balanced function. But as we'll see, surprisingly, right, a quantum algorithm, there is a quantum algorithm that can decide whether the function is a constant function or a balanced function with a single query, right? That means there's an exponential speed up, right? Because classically, you need 2 to the n over 2 plus 1 queries that scales exponentially with n. But quantum mechanically, you need a single query. So somehow quantum computation is able to produce 2 to the n over 2 classical bits of information by just doing a single measurement, single query, and that's an exponential speed up. This is the first example of exponential speed up. And how can we do that? Now let's consider the circuit, and we claim this circuit, achieves this result. So again, in the input, we have zeros, n bits of cat zeros, and as ancilla bit, right? Because we want to use the phase oracle construct, we have 1. And Hadamard, we apply Hadamard on these n qubits 0. And so this way we obtain a superposition, an entangled state of ket plus n of them, right? And this ket1 in the ancilla now through the Hadamard transform is converted to a ket minus. And we use this as an input to a phase oracle, U sub f. It's a phase oracle because the ancilla bit now is a ket minus state. And this ket minus state, goes to the output, as well. So let's analyze the circuit. So at stage 0 over here, stage 0 is here. In the input, we have ket 0 tensored n times, right? We have n of them. Tensored with ket 1. Ket 1 is the ancilla bit. And now, to get to stage 1, we apply an Hadamard, Hadamard tensored n to n of these qubits, and an additional Hadamard, right, to on this ket 1 state. So at stage 1, what we have is remember the Fourier sampling. Again, it comes. Just last lecture we had discussed how Hadamard transformed, the Hadamard tensored n times transform, an input ket 0, 0, 0. So it was linear superposition of ket x, of all the possible values of x, with this normalization constant in the front. And then we have tensored ket minus due to this ancilla bit. Now at stage 2, we apply this to this phase oracle. Remember what phase oracle does is it brings the result of f of x as an exponent, to compute the phase, corresponding phase. So after the phase oracle at stage 2, what we have is -1 to the f of x, ket x, tensored with ket minus, because this ket minus state is also here in the output. So now let's look at this output of the phase oracle. If f of x is constant, in other words, for all values of x, if f of x is either 0 or 1, right? If you look at it over here, f of x is 0, either 0 constantly or 1 constantly, we have -1 to the 0 or -1 to the 1. So that is a plus or a minus, right? -1 to the 1 is a -1. -1 to the 0 is a +1. So in case f of x is a constant, right, this output of the phase oracle becomes this plus minus linear superposition of ket x. We also have, of course, this normalization constant in the front. I neglected over here, but there's also this normalization constant in the front. Multiplied tensored with ket minus, because we have this, ancilla with ket minus is coming out. But in the case when f of x is balanced, right? So that means f of x for certain x, it is a +1, and for certain x, it is a 0. So depending on the value of the x, we have -1 to the 0 or -1 to the 1. So that means, but in this case, in the previous case, when f of x is constant, we have either a plus x state or a minus x state, right? But when f of x is a balanced state, we have all the other states. So at stage 3 now, we apply the Hadamard again, Hadamard tensored n again on this state. So let's take the two cases separately. Let's suppose f of x is constant. If f of x is constant, when we apply Hadamard tensored n to this f of x constant state. Remember, Hadamard tensor n is also inverse, because Hadamard is an also inverse of the Hadamard transform. So it's a unitary transform, and the inverse is itself. It's a self-unitary transform. So if we apply Hadamard tensor n to this superposition state that we obtain when f of x is constant, we revert it back to zeros and ones, right? Because as we said, it's an inverse transform. So if it is plus minus cat 0, 0, 0, right? Because when you apply Hadamard on this linear superposition cat x state, you obtain now your original input state, which was cat 0. And we also have this plus minus 1, plus minus signs in the front. So when f of x is constant in the output, when we do a measurement, right, on this, in the output, on the state, we obtain all zeros, right? After the measurement, we obtain all zeros if f of x is constant. On the other hand, if f of x is a balanced function, and we apply this Hadamard now tensor n on the output, right? We have Hadamard tensor n applied to linear superposition -1 to the f of x, cat x, and we also have cat minus, the ancilla bit tensor. So other basis state configurations other than cat 0, 0, right? This Hadamard transform would correspond to this kind of an output. In that case, we deduce that we have a balance function, any other string other than 0, 0, 0. So in conclusion, what we have seen is a classical algorithm requires order 2 to the n with the exponential complexity number of queries, right, as we discussed. But quantum mechanically, this circuit, there is a quantum mechanical algorithm through a single query, right? In this circuit, we have a single query. With a single query, phase query, we can compute or deduce whether this function is a constant function or a balanced function. So there is an exponential speed up. On one hand, it scales 2 to the n exponentially. On the other hand, you just need a single query. But we also have to note, that there are classical probabilistic algorithms that are easy, that are much better than this, that can decide with high probability whether this is a constant circuit or a balanced circuit. But in this case, we don't consider probabilistic classical algorithms, just deterministic classical algorithms. So I think more precisely we should say, with respect to deterministic classical algorithms, using this quantum circuit, we can achieve an exponential speed up. The next early algorithm I'll discuss today is the Bernstein-Vazirani algorithm that was introduced just after the Deutsch Josza in 1994. And the circuit is also very similar, as we'll see. The problem is as follows. Now we are given a black box function again that maps n-bit strings to a single bit. This is the mapping. But this time we have some specific information about f of x, the oracle. F of x equals s dot x, right? When you have an x as an input, it computes the inner product, s dot x modulo 2, and outputs, this inner product for an unknown s. We don't know s. And the purpose of this algorithm is to determine what s is. S is actually the circuit, right? Is the itself. This inner product is the circuit itself. In other words, f of x equals s dot x equals s1 x1 plus s2 x2 plus dot 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 s sub n x sub n modulo 2. This is what s of x is. Again, as we have seen, x is an n bit string, and s is also an n bit string, but we don't know s. This is the black box model. We don't know s, but we want to compute what s is with the minimum number of queries. That's the problem. Classically, we need n queries, right? I mean, it's obvious to see, because to definitively know what s are, s1, s2, s sub n are, right? You need to have n queries, because for each query you can deduce only one, s, right? I mean, let's suppose you in the input you have f1 0 0 0 0, right? So if you have f1 0 0 0, what the circuit will compute is s1 only, right? Because all the other x's are 0, only x1 is 1. So what the circuit will output is s1 only. So similarly, all the other s's require a separate query classically, right? For instance, f01000, right? If you put x as 01000, all the terms would be 0 except for this s2 x2, right? So this would return the value of S2 up to S sub n. For S sub n, if you input f of 0001, this time x sub n is 1, all the other x's are 0, then this would return S sub n. So classically, it's obvious, that you need at least n queries to be able to determine what S is. But now let's consider the circuit. This circuit is very similar to, it's actually the same circuit as Deutsch Josza's algorithm, except that now this oracle u of f, u sub f is different. U sub f now is, we have a defined form. U sub f is now f of x equals s dot x, right? It computes the inner product. So let's analyze the circuit and see how it works. Now over here, as we said, u sub f is a phase oracle. It's a black box for phase query. We say it's a phase query because the result of the function, right, comes in the phase. That's why we call it a phase query. At step 0, right, we have in the input cat0 tensored n times in the input. Since it's a phase query, right, the ancilla bit now is cat1, but I'm going to neglect this because it's carried out all the way to the output as cat minus. It's just a tensored cat minus. So just for a clear expression, not to complicate things unnecessarily, I'm just omitting, but you can assume there's a tensor cat minus state is carried out. So at step 1, again we have Hadamard tensored n times on these cat0 states, and as we discussed in the Fourier sampling primitive, right? What this does is applied on cat0 tensored n. What this Hadamard gate does is it just computes a linear superposition of all the possible cat x states with this 1 over 2 to the n over 2 normalization constant. So it's a uniform superposition of all cat x n-bit string states. So at step 2, remember, is the phase query. We apply this oracle, phase oracle. And as we discussed, the output of the phase oracle, it's just this normalization constant. linear superposition of all ket x states, but the phases -1 to the f of x phases, right? This was how a phase query or a bit oracle worked. But now we have a specific description of f of x. We know f of x equals s dot x. This is given. So at step 3, now we applied another Hadamard. Another Hadamard tensor n. Now this Hadamard tensor n on this state would produce a ket S state. Because remember now Hadamard tensor n is actually inverse, of itself inverse Hadamard tensor n. So what this does is, if we have S in the input, right, ket S in the input, and if the Hadamard transform produces this quantum state, that means if you apply the inverse operation now, which is the same as Hadamard ket n, you would obtain the input state back. So in other words, Hadamard n tensor n applied to this quantum state would produce the ket S, state vector. So and stage 4 now is the measurement stage, right? If you measure ket S, which is ket S0, S1 up to S sub n minus 1, remember all these n qubit states now they are measured here, and they are measured as S sub 0, F sub 1, S sub n minus 1 as zeros and ones. And in conclusion, and this is what we wanted, right? I mean, these S's, this S vector is what we wanted to measure. So in conclusion, classically, right, in order to obtain this S sub 0, S sub 1, S sub n minus 1 values, that represent this function, unitary function that we wanted to deduce, right? Classically, we needed order n, n queries, right? To identify each S sub I, we had to have a separate query, n queries. But quantum mechanically, using this quantum circuit, we only needed a single query, which is this, right? Which is this bit oracle, phase oracle. So using a single query, we were able to compute what S sub I are. In other words, using somehow, using the superposition state that we obtained through this Hadamard tensor n, through this operation, we were able to compute all these possible input states simultaneously. We were able to apply all these possible input states in some sense simultaneously to this unitary transform and measure, do a simultaneous measurement. So that resulted in an n-fold speed up with respect to the best known classical algorithm.